The purpose of this video is to show you how to graph a frequency spectrum. So you take a time waveform, and using a computer and a program like MATLAB, you want to graph the corresponding spectrum. We often want to do this. Quite often it's useful to understand what's happening in a system to look at the spectrum of signals. Quite often also when you're designing systems, you need to know things like bandwidths of signals and so on, and you can find that through graphing the frequency spectrum. So another thing that you should understand is that signals inside computers are sampled. Computers can't represent continuous time signals, except for some that you can represent mathematically as a function. But almost all the signals you use are sampled. And quite often we have enough samples that when we plot things, the lines look nice and smooth, but you have to remember, keep in the back of your mind, that they are sampled. So this picture shows graphically what we want to do. We want to take a time signal and compute, in this case I've shown its magnitude spectrum. The way we do this is with a mathematical process called the DFT, which stands for discrete Fourier transform. And the DFT is extremely useful. It allows us to manipulate things that start off in the time domain and put them into the frequency domain in a computer. Now, in both the time domain and the frequency domain, we assume that, or we will start with a time domain signal that's sampled and finite, and we will get a frequency signal that is also sampled and finite, which is good because infinite signals are hard to represent in a computer, and signals that aren't sampled are hard to represent. So let's illustrate this process by actually sampling our time waveform. And hopefully these samples are evenly spaced. When we do the DFT, this will give us samples in the frequency domain that correspond to the spectrum of our signal. Okay, you'll notice I have a finite number of samples. I have both in the frequency domain and in the time domain. So in principle we're done, because all we need to do is know how to make MATLAB compute the DFT, which we'll get to in just a minute. And so you take a time signal, you compute its DFT, and you're done. But it turns out it's very helpful to know what the time values are that correspond to each sample. Because if you don't know what the time values are that correspond to each sample, it's quite difficult to graph the signal accurately. We need that both in the time domain and in the frequency domain. So we will spend just a minute talking about what the values for these equally spaced samples in time and frequency are. If it doesn't look like it on the picture, just imagine that they're equally spaced. In the time domain, the distance between our samples is given by t sub s, where t sub s is the period, or the time, between samples. The frequency of sampling, f sub s, is 1 over t sub s. So sometimes you're given the interval between samples, t sub s, sometimes you're given the frequency with which you're sampling, which is f sub s. But you can compute one from the other. We will call this time where the last sample occurs t max. And so you can see, and let's assume that we have n samples. Okay, in this case n would be 9 if I counted my dots correctly. So you can see that t max is equal to n minus 1 t sub s. I have n minus 1 because that's the number of intervals I have between samples. If I have 9 samples, then I have 8 intervals between samples. So this is a useful expression. Most of the time you know what n and t sub s are, or you know, for example, what t sub s and t max are, and you can use two values to compute the other one. Okay, so that gives us what we will need to know to compute a vector of time values that we will associate with the samples, the time samples in a graph. We need to do the same thing for the frequency. From the sampling theorem, we know that the largest frequency we will have is f sub s over 2. That's the largest frequency we can represent with a sampled signal. And this means that the other end of the spectrum will be minus f sub s over 2. And you'll notice that the distance between these two is f sub s, which means that the distance between each of these individual points is f sub s over n minus 1. Okay, so that basically gives us a formula that we can use to figure out what the interval between samples is. We know what the lowest and highest frequency values are. So basically, we're done. We've got all the formulas we need. So let's see if we can actually do this with MATLAB. Whoops. Okay. So the first thing we need to do is I need to change MATLAB's working directory to a folder that I have placed a .wav file in. MATLAB has a function that reads WAV files. So I've created a file called whistle.wav, and it's basically I whistled into my microphone for a quarter of a second. And this will read the data out of that file and store it in the vector x. Okay, so I've read it. Now I need to know how many samples I have. I can do that by doing size of x. So it turns out by looking at this, I have the number of samples is 11,264. Okay. Now I also know, because because of the program that I used to record the whistle, that the sampling frequency is 44.1 kilosamples per second. This is the sampling rate that CDs use, by the way. And from this then, I can compute t sub s as being equal to 1 over f sub s. And I can find that t max is equal to n minus 1 times t sub s. Okay, so I think I've got all the information I need to plot this signal both in the time domain and in the frequency domain. So let's see if I actually do. I first define a vector t that goes from 0. It starts at 0. It increments by t sub s, and it goes to t max. And now I should be able to plot t comma x. And there it is. This is a plot of the whistle. And if I zoom in a lot, you can see that this function looks pretty much like a sine wave, except that its amplitude seems to change. It turns out that I'm not very good at whistling a very steady tone. So it looks a lot like a sine wave, but its amplitude is changing somewhat. Okay, so that's the plot of the time signal. Let's see if we can plot the frequency, the spectrum of that. So we start with f equal to minus fs over 2. It then is incremented by fs over n minus 1, and it goes to fs over 2. And now we should be able to... Oh, now we have to take the Fourier transform, the discrete Fourier transform of x. The way you do this, and I'm not going to spend a lot of time, I don't think I've got a lot of time in the video to spend explaining why I do it this way, is z, I'll call the Fourier transform z, is FFT shift of FFT of x. Okay, so now I can plot f z. Whoops. So what this shows me now is the real part of the Fourier transform. Now you've got to remember that Fourier transforms are complex, so this is probably not what I really want to have. So what I really thought I wanted to have was f comma abs of z. This gives me the magnitude spectrum. And so when I do that, I get something that looks like this, which is about what I was expecting to see. If we zoom way in on this, you can see that we have a peak in the frequency at about 1600 hertz, which is the frequency at which I whistled. And then we have a bunch of little stuff around 0. This represents the fact that the amplitude of the whistle was changing very slowly. So there you have it. Now, one last comment, or one last, well, we're pretty much done. If you would like to be adventurous, try computing z without the FFT shift and see what you get. It turns out that's a consequence of the fact that the DFT is well, actually it's a consequence of the fact that the DFT assumes that signals are periodic. So hopefully that's a topic for another video. And since my phone's ringing, I'll stop.